folks. Good morning, Megan.
Good morning.
Good morning, Sophie. Good morning, Jordan. All right, it's 11:10. So hopefully you enjoyed your weekend with no chemistry. You will get some homework tonight. I don't know if it'll be the entire worksheet, but you are going to get some homework tonight. In preparation for next week, I'm going to give you an assignment that's due next week, Tuesday. And that assignment is to change your name to a picture because on Zoom, because we're going to have students in class and students at home, it's helpful for your classmates if they have an idea of who they are talking to, because some of you may not know each other. So I'm just going to show you how I changed my profile picture. So you've got a week to find a picture of yourself or take a picture of yourself. So I'm going to share my screen. So it's really not too hard to do. When you go into Zoom, get that out of there. When you go into Zoom, up in the little corner here, Megan, you'll just see like your name or a letter like M, okay? So you click on that and then it says my profile. If you click on my profile, then you'll see a bigger thing and then it'll say change or delete. So you can go in and you can upload a picture. You might have to crop it because it's got to be under 2 megabytes, which is, as you know, Ray, a million bytes, because anything mega is a million. So keep your picture below 2 megabytes or 1 times 10 to the 6 bytes. You might have to crop it a little bit and then upload your picture. Because that way, when I want to make sure that the students at home are engaged and connected. So it'll be helpful if we can all see your faces. Even if it's your camera's not on, we can at least see what you look like. All right. So you got a week to take care of that. By the way, that's me in Iceland. I was backpacking in Iceland. Any questions for the good of the cause before we dive into the objectives for today? All right, we'll switch over to the iPad. All right, power model. Okie dokie. So we left off on that cliffhanger about the Rutherford experiment. So I know, Joey, you were probably losing some sleep over it, but don't worry. Today, we're going to let you in on the secret. So Rutherford was doing this around 1902. He had a radioactive source that was shooting alpha particles. Now, alpha particle, that's the Greek letter alpha right there. An alpha particle is a helium nucleus. So that's where I wrote 4,2 helium plus 2. It's a helium nucleus. In fact, maybe I'll just write that up there. An alpha particle is a helium nucleus. And they were shooting those alpha particles at a thin piece of gold. And the hypothesis was, and I think it was Jacob who said this, was that it would just rip right through the gold foil. Okay, that's one hypothesis. And I said that we would check out, see what happened today. Now that we have this all loaded up, I'm actually going to switch back to my computer so I can show it to you on the computer, because the computer is much better, the video.
Quality writing makes your schoolwork better and helps you stand out in the process. Meet Grammarly, the digital writing assistant that helps students create effective writing.
All right, so I'm going to maybe skip through a little of this stuff.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now, Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy, positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the center of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil.
You can't see the openings on this side.
Which is about 1.5 microns in thickness. And they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology.
So he's shooting these particles, should go through the gold foil, through the other
detector technology,
through the other side. So it's going to go through the gold foil. On the other side is a detector. He's got a second detector here that he's going to swing around just to see if any of the particles bounced off the gold foil. So that's why it got two detectors. One to check for them going straight through, and another one to see if any of them are being bounced off. The fancy word for bouncing off is scattering.
Technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space. So the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus.
So you can see most of the particles are going straight through. Blessed.
Comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it'll just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing it at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference.
So I'm just going to show you one other video of his, this one right here.
While performing experiments on radioactivity, Ernest Rutherford bombarded fast-moving alpha particles on a thin gold foil.
So here's an animation. So those alpha particles are going towards the gold foil.
He observed the reflection of the alpha particles with the help of a screen. Now, according to Thomson's atomic model, an atom consists of a positively charged sphere with electrons embedded in it.
So again, at the time, they thought the atom had this plum pudding. So what would you think would happen if you fired a bullet at a balloon filled with plum pudding? Well, the bullet should go right through, right? If you're firing a bullet at a balloon filled with vanilla pudding, it's going to go right through.
So Rutherford expected that almost all the alpha particles will pass straight and only small deflections will be observed if there would be any.
And that's what happened for the most part.
However, Rutherford got totally contrasting results. From his experiment, he made the following observations. First, most of the fast-moving alpha particles passed straight through the gold foil. Second, some alpha particles were deflected through the foil by small angles. And the third point, some alpha particles were deflected by large angles. In rare cases, an alpha particle got deflected by an angle of 180 degrees.
Meaning it came straight
Based
back.
on his observations, Rutherford derived.
So what would you assume if you fired a bullet at a balloon full of vanilla pudding and the bullet bounced back and hit you? Would you assume that the balloon is full of pure vanilla pudding? No, you'd assume that there was something in there hard that the bullet bounced off of. And that's the same thing that Rutherford assumed. So he changed the model of the atom. He said there must be something hard and dense right in the center. He called it the nucleus. Now, the nucleus has got a positive charge. Well, the alpha particle has a positive charge. So he assumed that the nucleus must be positive and that like charges repel, and that's what was causing it to bounce off.
Derived the following conclusions from his gold foil experiment. First, since most alpha particles pass through the gold foil without any deflection, most of the space inside an atom is empty. Second, very few particles suffered a deflection from their path. Now this means that positive charge occupies very little space inside an atom. Third and final point, as a small fraction of particles got deflected completely by 180 degrees, all positive charge and mass of gold atoms are present within a very small volume inside the atom.
All right. I'm going to stop my share and go back to our notes. All right, so the fact that most went through, but a few were deflected, told Rutherford this, that by the way, 90% went straight through, 10% bounced off. So what that told Rutherford is that the atom is 90% empty space. Because 90% of the alpha particles went straight through. So because the alpha particles have a positive charge, he assumed that what was in the center of the atom had a positive charge, and that the electrons went around the atom, and that when the alpha particles, these little positive helium atoms, most of the time they went straight through, but if they got too close, the like charges would repel. And so the tiny, dense core called the nucleus had a positive charge. I'm going to actually change that to look like the alpha particle. So when I shot these positive alpha particles, most of the time they went straight through, but every once in a while they'd hit the nucleus and bounce back. So that's where we get the beginning of this kind of like solar system explanation of the atom. Your elementary school teachers probably said, oh, the atom is like the solar system. In the center is the nucleus. It has a positive charge. This is the reason why we have that solar system kind of idea of the nucleus, is because of Rutherford's experiment. Okay. Now, there is one really big problem with Rutherford's model, and he knows it. All the protons were packed together in the nucleus. Well, what do like charges do? They repel. So why would you put, and don't write this down, why would you put all of the protons packed together? They should want to repel. And why would you put all the electrons that are negatively charged outside the atom? They also would want to repel. So that's why Thomson had his plum pudding model, because in the plum pudding model, you can evenly spread out the charge, because you've got the electrons, negative, 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 and then you've got the positive spread all over. So the plum pudding model, in a sense, makes more sense because you're evenly spreading out the charge. Whereas Rutherford's model, and he knew it was a problem, all the positive charge is packed into one spot. The other thing is the electrons are negative charged. Protons have a positive charge. Opposite charges attract. So why doesn't the electron go whoop, straight to the nucleus? Why aren't they attracted? Why don't they just go right together? So that is a problem with the Rutherford's model. So he knows it, it's right there. The other problem with the Rutherford model is the spectral lines, okay? Let me just let somebody in. So you've probably seen a rainbow before. The water in the atmosphere splits apart the white light. And so you see the colors of visible light. Visible light is actually composed of red, orange, yellow, green, blue, indigo, violet, also known as Roy G. Biv, okay? Unlike paint, so if you mix all your oil paints together, if you mix all your paints together, you get brown, right? Light is not like that. If you mix all the colors of light together, it's white, okay? You can separate white light into its individual colors, okay? A prism does that. So a prism separates light into its individual colors. All colors of light mixed together is white light. And when we're all together face to face, we're going to do this little activity. Let me see if I can find a quick little video on it.
This is one of our.
Okay, I'm going to share a little video with you that kind of will explain the spectral lines better. It's kind of hard to talk about this stuff. All right, so you should see a guy standing there, and in front of him is a white bulb. Okay, so that light bulb right there is white. So what I know about that is actually giving off red, orange, yellow, green, blue, purple, indigo, violet light. Now you're saying, well, Mr. Strauss, I don't see red light or blue light or orange light being given off. You're crazy. All those colors of light are being mixed together, so we see it as white light. So think about, like, if you took all the colors and you mixed them together, like if you take all your paints and you mix together, you get brown. Now, what happens if you start removing some of the colors? What would happen? So
Our funnest demonstrations to show atomic spectra. I'm going to show the spectrum of an incandescent bulb, which is continuous. And then I'm going to show the spectra of 4 different elements: mercury, nitrogen, neon, and especially hydrogen. Hydrogen will be important in the labs and in many other applications. So to show a spectrum, what we use is called a diffraction grating. This looks like a piece of clear plastic, but it's not. It is actually a piece of clear plastic on which an image has been inscribed with dark line, clear line,
blah, blah,
dark
blah, blah,
font
blah. It's a prism, okay? It's basically a prism.
of a camera, and show you the view of this continuous source with a diffraction grating in place.
So he used his diffraction grating, also known as a prism. And now you can see the colors that are actually in that white light. And you see one color blends right into the next. So you start with red, it transitions into a lighter red, and then orange, which transitions into yellow, and then green, and then transitions into blue. It's one long smear. That's what we mean by continuous.
And what you'll see in the image is the image of the incandescent bulb itself, and then to the right and to
All right.
of mercury.
So I'm just going to fast forward here a little bit. So instead of using an incandescent bulb, now he's going to use a mercury bulb.
To look at a discrete spectrum of mercury.
So he's putting a light bulb in. Okay, it's a fancy light bulb, and that light bulb only has mercury in it.
Now what this is it's a discharge tube. It has mercury in it, and what I'll do is energize this tube, apply a voltage to the tube, and that causes the gas in it to emit spectral lines according to the spectrum of the element that we're using, in this case mercury. So I'm going to locate this, its proper spot, turn off the continuous spectrum.
So there's the mercury light bulb, and it's a bluish color. All right. Now, light is a little bit different than mixing paints. So all the colors, all the types of light together mixed makes white. Then they separated out the white light. Let's separate this one out and see what we see.
This is a mercury spectrum without the diffraction grating. Let me get it in focus here. It's a bluish colored spectrum. There are mercury vapor lights that are used as street lights. So this may look similar to this bluish tint to the mercury vapor. Now let's try it with the diffraction grating in place.
So when he put the prism on there, it separated it out. We see green and we see blue. And they're thin lines. We don't see that blur, that continuous spectrum of going red, orange, yellow, green, where it's smeared out. We see specific lines. Now, he's going to do another one. This is, let's see what element this is.
So this is nitrogen spectrum. And with the diffraction grating in place, we see a number of lines present, some red, orange, yellow, green, and a violet turquoise.
But some of the colors are still missing. It's not a perfect blend. It's more continuous than the other ones, but not. I think this might be.
And when the diffraction grating is in place, you see a large number of red and orange.
That's neon. Yeah, that's neon. Okay, here's a good one.
And when the diffraction grating is in place, you'll see three lines. The farthest from the central image is a red line. That's the hydrogen alpha line.
So red, blue, or turquoise, blue. So these are individual lines. It's called a bright line spectra. Okay. So what's causing these bright lines? What causes the continuous spectra? What causes these bright line spectra? So I'm going to switch back over to the iPad. Stop my share. So when you look at a hydrogen light, so a hydrogen light bulb, you'll get the following colors: red, green, blue, and violet. So those 4 colors. When you look at white light, you get all the colors, right? White light, you get all the colors. But for hydrogen, you only got 4 bright lines. And so the goal of science is to explain what's going on here. You may be like, who cares? That's not how a scientist works. They're curious by nature. And the discoveries usually don't affect society for about 80 years down the road. Again, quantum mechanics is what gives us cell phones. No quantum mechanics, no cell phones. No computers. Okay. All right. So the next thing is the photoelectric effect. Okay, that's a little bit blurry. So Max Planck was studying electricity in the early 1900s. They wanted to make a continuous current of electricity. Now he was looking at metals, and they knew that if they shined light on a metal, you could get electrons to fly off the metal. Okay. What if you wanted more electrons to fly off the metal? Well, Lucy, if you want more electrons to fly off the metal, it would make sense to just add more light. So what do you think happened when they added more light to the metal? More light yielded no extra electrons. So even though they put more light on it, more electrons didn't fly off. So Max Planck was pretty upset. So what he did was he played around, and he changed the frequency. So he's got high frequency, but little light. So he had very little light, but he just changed the frequency of the light. And then lots of electrons came off. So he was able to make a very good continuous stream of electrons, a very good electrical current, by changing the frequency of light. But now he had to explain why, how, okay? So don't write this down, okay? The next thing I'm going to write, don't write it down. Light is different than the other waves, like sound and earthquake, tidal waves. For all other waves, the energy is proportional to their amplitude. So don't write that down. The squiggly line means proportional to. So a 10-foot wave is going to have more energy than, a 20-foot wave will have more energy than a 10-foot wave, right? Same thing with sound waves. The bigger the amplitude, the louder the sound, the more energy it has. So for most waves, the amplitude determines the energy. But it wasn't that way for light. For whatever reason, the energy of light was proportional to the frequency. Okay? So I'm going to show you another little clip of the photoelectric effect.
Everybody knows Albert Einstein for his theory of relativity and the
Einstein did a good job of explaining the photoelectric effect.
Nobel Prize he won for it. He also... What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect. Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is...
So this is where quantum mechanics starts to get kind of crazy. So they all thought light was a wave, but if light was a wave, it would not explain why the electrons were jumping off the metal the way they were, proportional to the frequency and not the amplitude. So Einstein, among others, began to think that maybe it's not an either or. You know, we said either you're a particle or you're a wave. Maybe not. Maybe you can be both.
What if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions. So he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
Okay, let me just switch back to the iPad. So what Einstein did was he helped explain what the photoelectric effect was. And that was, instead of thinking light as a wave, think of light as these little particles coming down, and when they hit the metal, it struck the metal and caused the electrons to fly off. Those are electrons. So think of light as not as a wave, but think of it as tiny little BBs, tiny little baseballs flying through the air. And now you're probably saying, Mr. Strauss, that's crazy. And yeah, it does sound crazy, but think of light as a tiny little baseball flying through the air. And so they call those tiny little baseballs photons. Photons are packets of light. Or another way you could put it is a particle of light is called a photon. So just like we have protons, electrons, neutrons, think of a photon as no different. Okay? It's a packet or a particle made up of light. All right? So Max Planck set out to find out how proportional it was. And so he came up with a constant to turn his equation, or turn his proportionality into an equation. Now, when you discover something, Ryan, you get to name it after you. So this constant, they named after Planck. And so H is Planck's constant. And the number is extremely small. So small that Planck thought he was actually doing something wrong. He thought, oh, if I keep it up, this constant will actually disappear and my equation will actually be E equal to F. But as it turns out, you have to multiply it by his constant. And it is 6.626 times 10 to the negative 34th. It's a very small number. Joules times seconds per one particle. So per one baseball, per one cannonball, per one electron, per one proton. So that's what I mean by per particle, per one thing. So now we've got our second important equation. E equals HF, okay? This number is, I think, one of the 8 magic numbers in physics. So when we look at, there are some numbers in physics that have to be exactly what they are. If you change them slightly, atoms do not form, and therefore we do not end up with a universe. The speed of light is one of those magic numbers. It's like 0.229, it's 2.997 something, 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 something times 10 to the 8th. And it has to be exactly that. If you change it slightly, then protons and electrons won't form atoms. Planck's constant is another one of them. If you change this number just slightly, electrons and protons won't form atoms. And then you won't have molecules. And if you don't have molecules, then you won't have Sam Hack, because Sam Hack is made up of molecules and atoms. So it is one of those mysteries of physics of why these numbers have to be the way they are. One of the other magic numbers is the gravitational constant. All right, it is 11:55. So as it turns out, you're not going to have homework tonight. So, but tomorrow you will. I will go into I will go into Canvas and I'll change it. You may have looked into Canvas already, but there is no homework. I will change it. And then tomorrow, you will definitely get homework. Okay? So I'll stay on the line if you have any questions, but since we don't have any homework, I don't anticipate anybody having any questions, but I'll stick around in case you do. So have a great day and I'll see you guys tomorrow.
Thank you.
You have a question, Ray?